Hello, welcome back. I'm Jason. Today we're going to get up close and personal and really study what's going on inside of a common lighter when you strike it and make a flame. Specifically, we're going to talk about 4 or 5 major components. We're going to talk about the striker assembly itself. We're going to talk about the fuel, the combustion process, how it burns, and the heat and the light that come about. And I can guarantee you, especially when we look in slow motion, that something simple that just kind of like happens in a fraction of a second can look absolutely amazing, and we can learn a lot when we slow it down and really pick it apart. Now, the first thing I want to do is really get up and close and personal and look at the ignition process. So here is the lighter right here. You put your finger on the top part and spin it, and then push down the red thing, and then the flame happens. And most of the fun part, I think, is hidden inside of this shielding here, which keeps it protected from the wind and also so you don't burn yourself and things. So the first thing I did to really look at it, and I do not recommend that you do this, I do not think you should do this, I do it for you so you don't have to do it, is I took that apart. This metal piece kind of goes around like this, and with some pliers you can pry that off. And when you do, you can see inside that there's this spinning wheel here. That's where the flint is, and we're going to talk a bit more about what that is. The fuel comes out here, which is butane. We have the trigger that lets the fuel out, and then the burning process happens. So let's take a look in slow motion and see how this process really happens. I'll be honest, my jaw hit the floor when I started to look at the slow motion footage. This is somewhere around 3,000 frames per second. Notice how initially the shield around the sparks is in place and it kind of hides a lot of the action. And it looks like after the sparks dance and it's over, it looks like absolutely nothing happens, but then out of nowhere the flame pops up. Here I've zoomed in a little bit just so you can see the fireworks happening on such a small scale. It looks kind of like some sort of big bang or something, and you can see the sparks and the sparkles of the combustion kind of lingering after the flame forms. Here's an overhead shot of the second attempt here, and you can see again after the sparks, this amazing flame front begins to form, and you can see it looks like a ring or a circle that grows in diameter as it rises up, eventually pinching itself off and forming the intact flame that we all sort of see with our naked eyes. I couldn't resist zooming in just a little bit so you can really see the detail in the sparks flying up out of the igniter, and then that flame front forming as a circle rising up, almost like a smoke ring, but it's sort of a plasma ring of heat and fire as the flame rises and begins to take shape. Now this is really incredible. What I did here was remove the shielding around the igniter so you can really see all the sparks, and I also strike the circle and rub the flint over and over again before igniting it to rub off some of that ferrocium to make a bigger spark. Here's a replay of a zoomed in version of the same thing. Notice how much bigger the sparks are and how much more full and sparkly it all is by rubbing off more of the flint before actually striking. Also, look at this flame front. It's almost forming like a mushroom cloud of light and heat as it rises up, and we just don't see this with our eyes. I just couldn't resist doing this again. This is a separate shot, similar deal. I was pre-rubbing the flint, making more sparks. I want you to notice after the sparks go down that the flame forms almost like a cylinder. It looks like the brighter regions are around the periphery of that circle, almost like it's burning from the outside in. Now here I began playing with the lighting. I was turning down the lights a little bit to bring down the brightness of the lighter itself, to let the light from the flame and the sparks really shine a little bit, and I think you can see more detail in the sparks and the flame formation. Same deal here. By turning down the house lights and really adjusting the exposure for the very hot sparks, remember they're 3,000 degrees, we can really zoom in. Now this is at a higher frame rate of about 5,000 frames a second, so you can really see the formation of the plasma in the lighter. Now these incredible shots were done with my macro lens, which really zooms in and lets me get on top of the action to see every detail. And I'm really not joking. When I first looked at this footage, I audibly gasped because it looks so incredible, even on the monitor. Just look at the plasma and the light coming into maximum brightness and how it fades away. And notice how the sparking is still continuing where the butane comes out. You can still see it sparking and the leftover glow of the heat long after the flame is formed. Here's another attempt, similar situation. It looks like some kind of cannon explosion or something. And at this point, I'm really happy I made the decision to invest in all of these lenses for close-up macro photography because it really makes amazing shots. This might be my favorite shot of them all because I turned the lights down so you can really see the contrast and what is going on inside of the flame and with the sparks. And with the zoom level, you can even see the smoke rising up afterwards. Now, I don't know about you, but when I look at something so simple like this that we take for granted and slow it down and really study it, I felt very mesmerized by watching it. And so it kind of inspired me to want to talk about it a little bit further, okay? Now, there's a lot of different pieces to this. The fuel that's burning here is called butane. You've probably heard of butane. So we're going to talk about the details here, but just to get that out of the way, butane is a hydrocarbon with 4 carbons and 10 hydrogens. C4H10 like this. Now, before I get to showing you what butane looks like, let's take a simpler hydrocarbon, right? A simpler hydrocarbon is called methane. This is methane, and there is a single carbon in the center, and in these hydrocarbons, they have hydrogens and they have carbons. So we have a hydrogen, which are the white balls, stuck at these angles here to the central carbon. Carbon in general likes to form 4 bonds. That's one of the reasons why carbon is so important for life, because it is able to form these very long chains because it has so many bonding points to other atoms. And carbon and hydrogen really love to bond and share electrons. Each of these sticks represents a pair of electrons, 2 electrons, one from each atom, that are being shared there. That gets into quantum mechanics and why that happens, but that's what's happening when we have a molecule there, the bonding and the sharing of electrons that's happening. In this case, a covalent bond. We have other cases when we have ionic bonds with electron transfers. In this case, they're actually shared. So methane has the prefix meth. And so there's methane, there's ethane, you probably heard of, there's propane, right? You've heard of that. And then there's butane. And the prefixes just correspond to how many carbons. So you have methane, which is 1 carbon. You have ethane, which is 2 carbons. And so it would be a longer chain with more hydrogens. And then you have propane, which would be 3 carbons with the associated hydrogens. And then you have butane. And then it goes beyond there. So methyl, ethyl, propyl, butyl. Just remember that. Meth, eth, prop, butyl. And so this is methane. This is the simplest. This is in your, this is in your flatulence. Cows are releasing this. We're releasing this all the time. Methane's really, really stable. And it's also combustible and explosive, actually. So here is what butane looks like. This is what's in that lighter that's actually lighting down there. And notice it was methyl, ethyl, propyl, butyl. So there's 4 of them here. And notice they're at these weird angles. The angle that is happening here all comes down to how the electrons are distributed in atoms, and it gets into some quantum chemistry and things. But the angles have to do with how the electrons are filling up the orbital and how they're bonding to other atoms. I can't go more into that angle there without a whole lesson in chemical bonding. But anyway, there's 4 of them here. And notice that these connection points are bonds, again, sharing of electrons. And then everywhere else where there's an available spot, there's a hydrogen connected. So there's 3 hydrogens here, and then there's 2 more here, and then there's 2 more here, and then there's 3 more here. So there's 3, 4, 5, 6, 7, 8, 9, 10. And this is why I told you it was C4, that's 4 black ones, 10 hydrogens. And you can go beyond butane. You can go, there's pentane, and there's all kinds of things after that, longer and longer chains. And the longer the chains are, the more carbons there are, and also the more hydrogens there are. Because remember, the simplest hydrocarbon is this methane, and you have each carbon wants to have 4 bonds, and so you have 4 hydrogens here. In the longer chains, then you have the 4 carbons. Some of the bond points are taken up by connecting to the next carbon atom, so the interior carbons only have the 2 hydrogens, but the ones on the end have 3 hydrogens. In any case, every carbon really likes to have 4 bonds. Now, one thing I want you to notice is that these sticks here represent what we call single bonds. Single pairs. Single bond doesn't mean single electron, it means a single pair of electrons. And because of that, you can think of these things being able to twist like this. Now I'm going to put that down and I'm going to show you really quickly what a double bond might look like. So this is carbon dioxide, carbon in the middle, 2 oxygens. These are oxygens. And notice that it's not connected by a single stick here. It's sort of flexible and there's 2 of them, and that means that it's double bond. So this is a pair of electrons bonding carbon to oxygen and another pair of electrons here. So pair and a pair. And because there's 2 connection points like this molecule doesn't really spin on its axis. You can't twist it very easily like this. But with single bonds, the molecule can actually twist. And so you can think of this, if it were just sitting in a tank or something, it's like jiggling, like constantly all the time. And the longer the chain, like if you had 10 carbons with a lot more hydrogens, 50 carbons, then it's a really long chain and it's spinning and dancing and it can twist a little bit like this. You see this one on the end can twist a little bit, and this one on the end can twist a little bit, and this can twist like this. Now, what's going to happen is it's going to maintain the configuration to get all of these atoms as far apart as they can be, because this hydrogen has electrons around it, which are repelling the electrons around these hydrogens. So it's going to want to, I'll turn it towards you, it's going to want to spin in such a way that these are far away. Maybe it's more like this. I have to look at the actual angles to figure out, but it's going to reach a position that makes every atom far away because the electron clouds with each adjacent atom in the molecule are repelling each other. And same thing here. Theoretically, this molecule could twist to look like this, but it's not really stable like this because these hydrogens are so close to these, they're repelling each other, and so it ends up forming a shape like this. But you can imagine if you give some heat to this molecule and it jiggles a lot and it's shaking a lot and it's bouncing back and forth like this, sometimes it might get up here, but then the repulsion kicks in and it gets down here and it gets up here and then it gets down here. Most of the time it's like this, but occasionally it can temporarily pop up like that. All right, so that's butane. The reason I mentioned the jiggling is because I need you to think about molecules being these like really violent shaking going on, because at room temperature, things are really moving quite rapidly in a liquid or in a gas, and that plays into how exactly combustion happens. Now, hung on to the end of these carbons, what do we have? We have hydrogen. You might already know that hydrogen is highly combustible, but it's already bonded to this carbon. But what if there was a way to just separate or pop off this hydrogen so it was freely kind of like hanging out like this, and then an oxygen comes with it to combust with it? Then it would form what we call a chemical reaction, and that is basically what is happening when we burn things. So I'm talking about butane here, but in general it happens when we burn anything. If you have this methane, it's a carbon with all of these hydrogens hanging out, right? And so if you could pop one of these hydrogens off and have it react with the oxygen, what would happen? Well, it would form water, right? Because this, remember, the red is the oxygen atom, and the oxygen is floating around the air. It's also double bonded as O2, so oxygen is bonded to another oxygen. I ran out of red ball, so I can't show you an oxygen molecule. But in the air, it's not just single atoms of oxygen, it's O2, 2 oxygen atoms bonded together, right? Well, what happens is when things burn, the oxygens separate. When you give them enough energy to break the bonds, they separate. And then one of these hydrogens, or one or more of these hydrogens pops off of the fuel, which in this case would be the methane. And if you get 2 of these to pop off, that's 2 hydrogens, and then that oxygen molecule separates and it comes in the middle and you get H2O. And what you would get is a water molecule. All right, so this is the 2 hydrogens that popped off of methane or butane or whatever you're burning, and the oxygen's in the air, and then it bonds and forms water. Water, as you might have guessed, is incredibly stable molecule. Very, very, very stable. And what I mean by that is you can break water apart. You know, we can use electricity to break water apart and such, but in general, water, I'm not talking about solid liquid gas. I'm talking about the molecule of water, H2O. It's what we call already at a very low state, energy state. The electrons and the configuration of H2O is very low energy. That means it's already reacted and the electrons and the atoms are configured in such a way that it's already at a low energy state, like being at the bottom of a mountain. You're at a low energy state at the bottom of a mountain. It takes a lot of energy to walk up that mountain. But if you roll a rock all the way down the bottom of the mountain, it's at a low energy state. It's not going to spontaneously go up the mountain because that requires work, energy to put into that to make it go to the top. Water is like being at the bottom of the mountain. Also, carbon dioxide. This is carbon dioxide, 1 carbon, 2 oxygens. Notice that they're double bonded like this. It's in a low energy configuration. That means they're stable and they're not likely to be broken apart unless you put a lot of energy into it. And it has to do with how the electrons are configured when they form those molecules. So carbon dioxide and water are very stable products that are almost always formed when you burn something. All right? And so what we do is we take oxygen, which is 2 oxygen atoms double bonded together. The double bond means it's strong and it takes energy to break those bonds. And we put it next to methane or ethane or propane or butane, and we add energy, heat, to pop some of these hydrogens off, react with the oxygen that is broken apart, and form carbon dioxide plus water. Because if I burn this and I pop all these hydrogens off, the carbon is left alone, right? And the carbon is going to want to do something as well. What does it do? It forms, again, with some of the oxygen in the air to make carbon dioxide, double bonded, very, very strong, low energy molecule, and also water. So these 2 molecules are what are formed, water and carbon dioxide, in almost all burning of hydrocarbons. There's an exception I'm going to tell you about in just a minute. So here is our butane. Now, if we burn it with oxygen, it's O2, don't forget. This is a gas and this is a gas. I'm not writing it down, but they're both gases. And I'm telling you that because of what's going on here, what ends up forming is CO2 plus H2O, right? This is what forms, because what you have here is you have the butane, C4H10, you have O2, which is 2 red oxygens double bonded together right here. And then during the combustion process, some of these hydrogens pop off and combine with the oxygen, which also breaks apart. The hydrogens and the oxygens form the water. The carbon that was left over here also bonds with the oxygen and becomes carbon dioxide. So just to put a picture on it, the product that you get, or the products that you get for complete combustion, I'm going to talk about that in just a minute, is carbon dioxide and water. That's what you get. And these are very low energy stable molecules. These are like being at the bottom of a mountain. When it reacts, the reaction is going to proceed if it gets to a lower energy state. The electrons, as you might remember from chemistry or physics, they're in electron energy levels. You can have electrons very far away from an atom in a high energy level. You can have electrons very close to the nucleus of the atom in a low energy level. And that's literally analogous to being at the top of a mountain or the bottom of a mountain. And when the electrons reconfigure to form these products, they're closer and they're in lower energy state than they were to begin with. So these are more stable. They're not going to break apart spontaneously. That's why there's so much water on this planet. And also so much carbon dioxide on this planet too. But look at the Earth, it's almost all water. It's like 75% water because water is very, very, very stable. Now I left something out here. If you notice this, you have to have conservation of mass. We have 4 carbon atoms here, but we only have 1 here. We have 10 hydrogen atoms here, but we only have 2 here. We have 2 oxygen atoms, and that one actually matches. We have that here. Well, actually, no, we have a 3rd one, so those don't match either. And so this violates conservation of mass. So what we have to do is balance this chemical reaction. I'm just going to give you the answer and we're going to talk about it. That was the wrong one to use, wrong marker to use. If you put a 2 here, you can think of this being like 2 parts of this molecule reacting with 13 parts of this molecule, yields 8 parts of this molecule and 10 parts of this molecule. Now in chemistry, we don't call it parts, but that's a really good way to think about it. We call it moles. Moles is just a way to measure the number of atoms or molecules in a reaction. You can think of moles being like a unit of counting, like dozens. Like you don't always have to say you have 12 eggs, you just say you have a dozen eggs. You don't have to say that you have like 24 eggs or 36 eggs. You might just say you have 2 dozen or 3 dozen eggs. The dozen is like a unit of counting. In chemistry, we have something called a mole, which is just like a dozen. It's just much, much larger number of molecules or atoms. So you can think of it as dozens or parts or whatever, but what it means is that 2 parts of this molecule reacts with 13 parts of this molecule, yielding 8 parts of this molecule and 10 parts of this molecule. And now because you have two of them. 2 times 4 is 8 carbons on the left, and there's 8 carbons on the right. 2 times 10 is 20 hydrogens, and 10 times 2 is 20 hydrogens. 13 times 2 is 26 oxygens. Here, 8 times 2 is 16, but I have 10 more, so that's the 26 that add up here. With these numbers in front, these are literally like recipes. You don't measure sugar or salt in grams all the time. You might measure it in teaspoons or cups. It's just a unit of counting. And so when you arrange the reaction in these ratios, then the reaction proceeds. And it tells you how much stuff is required on the left with how much stuff is required on the right. Now, this reaction yields carbon dioxide and water, but it only happens if you have enough oxygen here to actually completely combust this stuff and make fully formed products. What happens if you burn this butane in an environment without quite enough oxygen? And this actually happens in the lighter flame. I'm going to talk to you about the different colors of the flame in a minute, and this dovetails in with what I'm telling you. But if you burn it in an environment without enough oxygen, then you don't get carbon dioxide. You get carbon monoxide. Carbon monoxide. And carbon monoxide is not CO2. Carbon monoxide is CO. Whereas carbon dioxide would be CO2, carbon monoxide is just a single carbon and a single oxygen. Mono means one. And so it's carbon monoxide. So it forms a molecule and it's stable. It's just not quite as stable as CO2. And it's because of the incomplete combustion if you don't have enough oxygen available. And when you're forming different products in your combustion, it leads to different colors of the flame that I'm going to talk about in just a minute. So we said we had our fuel. This is methane. In the actual lighter, we're burning butane. We said we have our oxidizer, in this case, oxygen. Now, something else is required. We have to give it some energy, give it some heat, and that's what the sparks do. They get very, very hot to give it some reaction energy to get started. That energy goes into jiggling this molecule, popping off some hydrogens, separating the oxygen, and starting the combustion process. But how that actual striker works is fascinating, I think, all by itself. It comes from an alloy called ferrocium. Now you might say ferrocium, ferrocium. It has the ferro at the beginning, which means iron, and the cerium at the end, which is an element on the periodic table. Now, it also has some other elements in there. So there's iron and cerium, which are on the periodic table. They're metals, and metals in general like to lose electrons. They're on the left side of the periodic table. In general, metals like to lose electrons when they react. There's also some lanthanum in there, some neodymium, which can be used to make magnets, some magnesium. Magnesium burns with a very brilliant, bright, white sort of flame. You can see the white is just so bright you can't even really look at it when magnesium reacts with oxygen. So all these things are mixed together and they call it ferrocium or ferrocium, however you want to say it. So what happens is when you strike the lighter here like this, what's going on is you're spinning with your finger the wheel. The wheel is in contact with this ferrocium rod, which scrapes against it, and it causes friction, and it splinters into a million pieces that go off like this. Now, when the cerium inside of there, which is a metal, gets broken up like that, and you give it some energy, and it's exposed to the air, it rapidly oxidizes. So it's a chemical reaction. So the cerium loses electrons. We say that that's oxidized. And it bonds with the oxygen in the air, which likes to gain the electrons, or it likes to grab them, and it forms something called cerium oxide. Now, that process releases a lot of light. And there are other things in there too. The iron is glowing a bit when you flake it off. The lanthanum, the magnesium is a part of it too. But the main thing that's making the spark when you're doing this is the cerium metal. And it's not just glowing like if you were to scrape metal on a grinding wheel, you would see sparks flying. That's not a chemical reaction. That's just glowing hot particles. The cerium is actually reacting with the oxygen. And there's a rod of it in there that's constantly under tension, is being pushed on the wheel. So as you keep spinning it, it grinds it down. Eventually you run out. Now this ferrocium is commonly called flint, right? That's a common word, but it's a mixture, it's an alloy of all of these different metals. And it generates sparks when it oxidizes rapidly in the thousands of degrees. I think it's around 3,000 degrees Celsius. And that is enough energy when in contact with the butane, which then comes out of the lighter when you put your thumb on the trigger there. that it's giving it that energy to separate the molecules, separate the hydrogens, recombine with the oxygen. And then once the reaction starts, you're generating a lot of heat from the burning process. And that heat is why you don't need to continually give it sparks all the time. Like when you light this lighter, you're not like always having to light it. It's a sustained chain reaction. And the reason why is because once it generates some heat, then that heat is what further jiggles the fuel that's coming out to continue the reaction, breaking apart the butane, hydrogen separating it, and the reaction can continue. So it has to create some heat in order to propagate and continue the reaction. So we've covered the sparking mechanism. That's a chemical reaction where the cerium is bonding with oxygen, releasing heat and energy. And by the way, why does cerium like to lose electrons so much to the oxygen? Well, it's because cerium is an atom on the periodic table with a lot of protons and a lot of electrons in the cloud. And those electrons, the outermost ones, are very far away from the nucleus, so they're not held on very tightly to the nucleus with the attraction from the nucleus. And because of that, they're very easy to be attracted by other things. Oxygen loves to grab electrons and hold on to them, and so it's just easy to strip them off of the cerium, and that's why it reacts so readily. All right. The last thing I want to mention to you is something called an energy diagram, and I already mentioned this in words, but basically you can think of this reaction being a graph, right, of the butane, right? And you can think of this as reaction, progress, right? And basically what's going on is the graph looks something like this. It has a hump and then it goes down like this. And this is the energy direction. This is high energy, low energy. This is just like being at the top of a mountain. You're in a high potential energy state at the top of the mountain. At the bottom, you're at the ground level or sea level, and you're at the bottom of the mountain. You have very low energy. If you are standing at the top, you can throw a rock off and it's going to spontaneously go all the way down to the bottom until it comes to rest. In general, the universe likes to go to states of lower energy. That's the way our universe seems to work. But the problem is there's an energy barrier in the way. You can, that's not a straight arrow, I apologize, but this is an energy barrier. In other words, the butane and the oxygen would love to react, and they would love to form the CO2 and H2O, the low energy products. But the problem is it takes energy to separate the hydrogen in the hydrocarbon and to separate the oxygen molecule so everything will react. It takes energy to do that. That means thermal agitation. And that energy is represented by this barrier. If you can just give the system a little bit of energy initially, then it will spontaneously roll down and combust. And when it generates its own energy from combustion, the heat propagates the reaction. But you have to get over this hump first. That's why the butane doesn't spontaneously combust. It doesn't have enough energy at room temperature to begin the combustion process. But by using that flint, we can give it 3,000 degree sparks, which jiggles just enough of the butane to begin the separation of the hydrogen. The oxygen can separate in the air a little bit, begin a tiny one or two of these things to begin to combust, generate a tiny bit of heat, and then the reaction proceeds all the way down into a stable situation with that flame. One more thing I wanted to mention were the different colors of the flame of the lighter. You have near the base almost transparent, no color, and then you have kind of a bluish color, and then you have a nice orange color, and then the flame is over. Now that, among other things, is basically dependent on how complete of a combustion that we have. I mentioned before that you have this big molecule, butane here, lots of hydrogens on it, and when it is burned, here with the oxygen, we get CO2 and H2O, but that's only if we have enough oxygens to get what we call complete combustion. That means if we break this molecule completely up, meaning all the carbons are totally separated to be able to form the CO2, and all the hydrogens come off so that they can form the water with the oxygen in the air, then every one of these atoms goes into CO2, every one of these hydrogens goes into the water. Of course, they need the oxygen from the air to do that. But the only way that complete combustion can happen is if the flame is hot enough to agitate this thing to make it happen, and also for there to be enough oxygen molecules available in order to do all the bonding to make the products. So in this case, the way I've drawn the reaction is we have complete combustion. And in complete combustion, we form CO2, as I mentioned before. But if you have incomplete combustion, you would have the exact same reaction except for one change here. If we don't have enough oxygen, we're only going to have carbon monoxide as a product here. So instead of the CO2 that we get here, plus the water that we have here, what will happen is we'll just have the carbon monoxide, which is one oxygen and one carbon there. And the different products that form correspond in part to the color of the flame. So when you look, when you see the bluish part, that's hotter, and that's the complete combustion of the butane. They're yielding the carbon dioxide and the water. That's more at the base of the part of the flame that you can see. But up above that, when the flame starts to just turn orange, it's actually a little bit cooler, and also you're having a lot of carbon monoxide form. And then above that, and scattered in there, is if you have even less oxygen available, then you can have what we call hydrocarbon fragments. In other words, this is butane, and so if you have complete combustion, it completely combusts. But what happens if, like, this pops off, you know, and another hydrogen's here, and you got a methane hanging out here that doesn't actually burn with anything? Like, maybe you have some of these molecules that break apart, but fragments, you know, are just kind of hanging out there, and they just kind of float up, but they don't burn because there's not enough oxygen, or it just doesn't come into contact with an oxygen molecule. Well, then you can get some of those fragments glowing, and just like we can put a piece of iron in a fire and it'll glow when the electrons start jumping up and down in their orbitals, you can have the same thing in a methane molecule that's not combusting. It can still glow a little bit. So in the tip of the flame, when it's coolest, you typically have a lot of unburned fragments of hydrocarbons that are just glowing a little bit. So the candle flame looks really simple, or the lighter flame looks really simple, but it's actually a lot of detail of what's going on in there with the different colors, complete combustion, and so on. I hope you've enjoyed this. I really like the idea of taking things that seem simple, you know, and really diving in, because you know, you can look at the simplest things, the things that most people would overlook and say, oh yeah, that's how it works, and really learn a lot just by studying it. And that's what I really like to do. I hope you've enjoyed it. Please drop me a line. Let me know what you think, and I'll see you in the next one. Learn anything at mathandscience.com.